Hi, my name is Julia Silly, and I'm a data scientist and software engineer at RStudio. And today, in this screencast, we're going to use this week's data set from Sliced, the competitive data science show on Kaggle, to highlight two main things. The first one is how to create a custom metric in tidymodels. The yardstick, which is the package in tidymodels that help you evaluate the models that you're building, has lots of different metrics built in, but it's also extensible in that it lets you build custom metrics that you may need. On Slice this week, the models were being evaluated on root mean squared log error, because what was being predicted is the price of Airbnb listings in New York City, and they're distributed in a in a very log normal kind of way, with lots of low to medium prices and just a few very high prices. And that's not a metric that's in tidymodels by default, but we can show how to make one. You first want to make like a metric, vector representation of any metric, and then you want to make a method for a data frame for it. So we'll walk through how to do that. The other thing I want to highlight is how to combine structured data like numeric predictors, categorical predictors, with unstructured data like text, and how to combine them as one so that you can use them together in predictions that you want to make. So in this case, that's the name of the Airbnb listings. So let's take all that together and then walk through how to build a model to predict prices of Airbnb listings.
Okay, let's get started modeling this data set of Airbnb prices. So I've got the train and data set here in my working directory. I hope. Train, yep, there we go. So I'm going to call this train raw. So like I said in the intro, this is the data set from this week's Sliced episode, and I thought it was pretty interesting for a couple of reasons. So let's get started first with a little bit of some exploratory data analysis, some visualization. So the thing that is being predicted here is this price variable, price here, and it is the price, the like nightly price of these Airbnbs in New York City. So if I do this, so notice that it is super skewed. There's just a few that are very, very expensive, but that lots are down here at this lower, at these lower prices. So this is, really common actually in a lot of different domains that we might work in. So it's really good to know how to work with this in a lot of different ways. Notice that we've got some there's probably some zeros or something in there, although honestly I've never seen an Airbnb that had a price of 0. Let's look at price. The mean is here. Let me stretch this out so we can look at it a little better. Price. Yeah, there are some 0 price Airbnbs in there, which that's a little strange, but okay. Some people will just let you come and stay there. Isn't that nice of them? So we'll say there's like a borough. Let's look at train raw. There's a borough here. I think it's called neighborhood group. And let's say alpha equals 0.5. Let's make fewer bins. So these are all on top of each other now. So let's make it position equals identity, like that. All right, so you can see how much more expensive the Manhattan ones are than, say, Brooklyn. So say in Brooklyn, if you're looking for less expensive, and Manhattan are the fancier, which I think this makes sense. Also, we can see the difference by number. So, you know, there's much fewer in Queens. If what you actually want to see is it by you don't want to see you don't want to see it by count, you want to see it by density. We can do that, which can be useful as well. Like both of those are useful, I think, but different views. And let's just clean this up a little bit more and say fill equals null and x equals price per night. Like that. And so I think we could do either count or density there, and both of those are useful and helpful. Maybe I'll take the count. I'll take the density out. Like that, because that gives us kind of a helpful view of what's in this modeling data set. We definitely have this, this logarithmic characteristic of the price that we're going to be modeling. And I think we should take that into consideration both in the modeling, and there's a metric that if you go here to this link, you'll see that the metric that they're evaluating on actually takes it's a log, a root mean squared log error. So we'll make a custom metric for that. Let's just make a map. Always fun to make a map of things like this. So we can start with just a nice basic map. Like, so we have longitude and latitude information. We can say color equals, let's say log price, like this. Say let's just put points on, a lot of points here. And let's say scale, color, one of the viridis. So this one is for, how does this one? This one is for color. This one is for these are for different options. So I think I want this one like that. So this will take a moment. Oh no, actually that was really fast. So here's New York. I love it. Manhattan, Brooklyn. You can see the park. Very nice. I love it. Well, let's copy, paste, and let's just change this a little bit. So instead of color here, let's change it to Z equals log price, and let's change it from points to stat summary hex, like this. I don't exactly remember how it works. Let's look. Stat summary hex. So I think the way we do it is we send in a function. That's right. So we send a function. We can do mean. So I guess if we do nothing, it'll just take the mean. And that seems like it will work pretty well. And I think we have to change from color to one of these other options, because we're doing it's doing fill now. So I think it's this. Let's see if that works. That did not work. It did not do the fill. It just used the blue color. So what have I done wrong? Scale, stat summary, hex, scale, color. It didn't do the viridis color. What if I do this? Does it do it? No. This I think is for discrete. It's not doing it at all. Maybe I have to give it a function, like mean or median. Come on. I want to do, silly, not in scale, color, scale, fill. There we go. I like this, but I can't see much of, so I could probably take this function out. Let's make this, let's make these bins smaller so we can see more of the city. That's looking pretty good. Labs fill equals, let's say, median price log. Let's make it like that. All right, that is looking pretty. I love it. So you can see the oh, that's not median, that's mean. Because I didn't give it any function, so it's mean. This is looking beautiful, and I love it. So you can still see the park here. You can see areas where there are not very many Airbnbs, and then we can see kind of these areas of very high Airbnb pricing, the areas of the low Airbnb pricing, and areas where there aren't any. So I think this is super dense in information, and I like it a lot. All right. Okay, so now let's move on and let's build a model. So we're going to build a model, and then we're going to talk about how to evaluate a model with a custom metric. So let's load tidymodels, if I can do this. And let's, so I'm going to split. I am going to split here because I want to use my some testing data here. So what I'm going to do, so this custom metric that they talked about evaluated on the log scale, but I want to train my model on the log scale. I don't want to train on that, on the price, on the original, the original scaling there, because it is so skewed. So I'm going to say mutate price equals log price, like this here, and then I'm going to do initial split. I'm going to say strata equals price, like so. So that will be on the log scale. So let's call this my NYC split here, and then I'll do NYC train. And then we'll do the same thing for make some testing data. And then let's make some folds. And I will say V fold CV, and it will make folds from the training data. I'm not going to do all 10 just so this doesn't run for forever. If I was training a model to like put into production or something, I would probably do all 10. But for being faster, like this is still a lot. This is still a lot. Okay. Okay, so now let's talk about feature engineering. So what is in this data? We've talked about some of the geographical information. Let's look at what else is here. We have some text information. The name, let's take a look at what we've got here. We've got the name, nice bedrooms and 2-bedroom apartment, small, tidy bedroom and duplex. We've got some IDs, host names, neighborhood group, which is like the, I already showed you that is the borough, neighborhood, which let's see how many there are of those. NYC train. So in the training data set that I made, there are 212, and there, some of them, there are very small numbers, so there might be even more that are in the test set. Latitude and longitude, which is what I use to make these maps. Room type, of which there are 3. Price, which remember now is on a log scale. Minimum nights, numbers of reviews per month, how many listings the host has, and how many nights it is available a year. So let's start putting together some feature engineering here. So I'm going to do a recipe where price, and so I'm just going to do a demo here. So definitely I'm going to do latitude and longitude. I'm going to do neighborhood. I'm not going to do the borough, neighbor. It was spelled, yeah, as if I were British, although this is New York City. Room type. I am going to do that minimum nights. I am going to do the number of reviews. I'm going to do that availability. What is it? There. And I am going to try to learn something from the name. So what I'm going to demo here is how to do some, how to combine a rectangular, what you might call, tabular information. I'm going to combine it with some unstructured text information that I will turn into rectangular information. Okay, and the data here is NYC train, like that. So let's see what I'm going to do. I'm going to say step novel on neighborhood, just to, in case there's new levels in the testing set. I'm going to say step other on neighborhood because that's too many levels. I'm going to drop the threshold though because it's set a little high for me, this. And now I'm going to do some text processing. So I'm going to load the text recipes package. And I'm going to say, I'm going to tokenize the name of the listing. I'm going to remove stop words from the name. I'm going to set a token filter on the name, meaning I'm just going to keep, there's a couple ways to do it. I'm going to just keep the top, I'm going to go low here, just real low, like 20. I'll do 30. I'm just going to keep like only the top 30 tokens after removing stop words just to get something working here so I can demo this. And then I could weight by term frequency or by TF-IDF. Either one would be a good starting place here. I'll weight by with 30, I might as well do this. We're not really doing that much here. We're just kind of getting that information into the model. So let's run this. And just so I can show you what this looks like, let us prep it in NYC recipe. So what it's doing now is it is making sure we can handle any new factor levels, collapsing factor levels, and then it's doing these this handling of the text data. And let's show you what it looks like on what the output looks like. So we've got latitude and longitude. We've got these other levels that have been replaced for the infrequently used levels in neighborhood. And then these things look the same as what they did before. And then we have all these new variables. So about 30 of them. Things like bright, cozy, NYC, room, studio, village, loft. So if those are in the name of one of these Airbnb listings, they get a 1 or a 2. This had home twice. And if not, it gets a 0. So these are kind of like indicator variables now, is basically what I've created, like 0s and 1s here. So that is the data that we're going to use as the input. So for a model, I'm just going to start really sort of basic with a bagged tree model. I like this for getting something started. So I'm going to do a bag tree. Let me load this. So I've got it. Bag tree. I'm going to bump up min n just to, get something going. I'm doing a classification tree here, and I am going to I'm not even going to go very high here. I'm going to do 25 and set mode regression because I'm predicting that price. I'm predicting it on a log scale. And let me make a workflow here. I'm going to call it bag workflow. So I say workflow, and then I will say add a recipe to it. It's this NYC recipe. A recipe. And then I'm going to add my model, which is my bag tree here. And then I'm going to set a seed because it's doing bootstrap aggregation for me. And I am going to say bag fit. I'm going to fit the workflow to my training data. So I'm just going to fit it one time, this bootstrap aggregated tree one time. So this kind of model has a lot in common with a random forest, a lot in common with XGBoost models. It's based on trees, but it is Oops, it did not work. Oh, right. Oh, gosh. So there's zeros in there. So I'm just going to add $1 to all the prices. So let me try that again. So since I'm dealing in dollars, adding 1 isn't that unreasonable of a thing to do. Adding 1 when you transform something on a log scale with the zeros is not something that the statisticians in your life are going to be very happy about, but I think it's a reasonable choice in this case because I'm dealing with dollars. Okay, so the great thing about a bag tree model is you get variable importance scores for free because you say like how many times was it used, like how important is it in all the splits. So room type, super most important, like is it the whole apartment, is it just a room? And then we've got this, like these things are where it is, latitude, longitude, neighborhood. Then we have information about that came from the name, room, then private. So this is probably, these are probably things that drive the price down. Private room, minimum nights, availability, number of reviews, studio. So is it a studio apartment? I don't know. That probably drives it down. I'm not entirely sure, but this is the information we have on what is most important in the scores. So we fit this now one time. So how do I know how good this model is? And if I was competing on Sliced, how would I know how well I was going to do relative to other people? And if I was, trying to put this model into to evaluate it in the real world, how would I know how good of a model this is? The way that I know that is by using those resamples that I made, fitting it to all the resamples where I have analysis sets and assessment sets, and I fit them to the analysis sets, I evaluate on the assessment sets, and I see how they did. So I'm going to fit that same model, I just fit one time, to all of these resamples, these folds that I made. Let's call this bag results, like this. And then I will collect metrics on them. Bag results like this. So let's run this, talk about what's happening here. So I set up to use the parallel backend on my computer. So what's happening is for these folds that I made, 5 times I'm going to fit the model on these observations and evaluate on these. Fit the model on these observations, evaluate on these, and go through and do that 5 times, and then I will have 5 estimates of performance for my model. So it will, you saw how long it took to do it one time, so it will take 5 times that long to go through and do that. This is a model that goes, that is pretty quick. This is a pretty big data set, so it will go through and do that. And then after that, what we will do is we'll look, I just use the default metrics, notice. Here we go. Okay, so I just use the default metrics. So what this RMSE here is, it's root mean squared error. So it's root mean squared error on the log scale. So now this gives me a pretty good idea of how I would do relative to other people, and certainly relative to like if I changed the model, I could understand if it got better or worse. The thing is that on Slice last night, they weren't evaluating on root mean squared error on the log of the price. They were actually evaluating on root mean squared log error, which is different. So let's walk through, let's get some test data first where we have predictions, then let's walk through how to make a custom metric. So I'm going to use augment on that bag fit. Remember I fit it one time to all the training data. And so I'm going to augment onto that testing data I meant. Let's call that test result. So let's do that one time. So remember, I'm still on the log scale here. I'm on the log scale. So I'm making a prediction. Test RS like this. So I have the price here. and the prediction here, and those are both on the log scale. So I can in fact make a graph here and show this to you. So if I put price, pred, let's see, let's make geom point. There's still kind of a lot, so I'll set the alpha lower. Let's put let's say put the slope equals 1 line here. Color, let's make it gray. Let's make it transparent. So let's look at this. So, oh, that didn't work at all. There's no points. Why didn't this not work? Oh, I need a plus. Okay, now there's points on the line. So they're close to, you know, like that's how well my model is doing, just this first model. So it's an R squared of 0.603, you know, so that's how well I'm doing based on these predictors that I have. But notice these are still on the log scale, the log of price. So I can do X. I can take, oops. I will take these up to the e to these values, and then let's, just so we can see this, I think this will be interesting. Let's put the color there, and now if I plot this, everything's going to be squished down again because I'm taking it off of the log scale. So let's do scale X log 10, scale Y log 10, and labs color equals null, like this. Okay, so now I put it back on the price. I put it back on real price here. So I can do, I can put those on dollar. I can put that here just to emphasize. And so X equals, so this is the true price and Y is the predicted price, like this. And you can see like we've got more of that green color for Manhattan up at the higher prices, you know, other boroughs down here. So this is looking pretty good. So, and this shape here is showing us, you know, we've got some heteroscedasticity, like where we have like more spread at the higher prices, which is really common in my experience when you train a model like this, where you're trying to predict a price or something that's like log normal. But okay, so if I want to know how am I doing, especially on the specific metric that say sliced was going to use, is this it? This is not it. This is close to it, but this is actually not it. So if I want to make a metric, I can do that in tidymodels. So we have a article here on tidymodels.org about how to develop your own metric, but I'm going to walk through how to do that here. So we do need the rlang package loaded in order to be able to do that, to be able to get this through. So let's, the first thing we need to do is we need to make a vector representation of the metric. So we, instead of RMSE, we have RMSLE. And we're gonna have RMSLEvec like this. And it's, here, let me do this because it's, I don't make mistakes if I do this. There we go. Okay, RMSLE vec like this, and the let's look at the RMSEvec function just so we can copy some of this and get it right. So it will have the same inputs here. It will have this metric set here will be the same, except instead of RMSE, it will have the L. So we're gonna make this. This will be for us. that we are going to make right here. It's going to be a function of truth and estimate. And instead of, if you go up here and click through, the thing that's different is, and instead of truth here, it is, let me make sure I can get this right. Okay. It's the log of truth plus 1, and an estimate, instead of here, we have the log of estimate plus 1. And so the reason why it's not the same is because of how these squares and means and square roots and everything. So the reason why RMSE on the log scale isn't the same as this is because of how this math works out. Okay, do we change everything? RMSLE, truth estimate. So this is a metric vec template. We can make this look a little bit nicer. And we need the dots here, I believe. Okay, so we've got now our vector implementation. So this, if we were to put a vector here and a vector here, we would get out a result, like one number. So now what we need to do is we need to make a generic RMSLE. Let's make a function again. RMSLE. So this is, we pass data in here, and let's do use method for RMSLE. So we're making a generic, and MSLE, we're going to say new numeric metric, because it is it's something that works on numbers, not on classes. MSLE, it's a function of this function that we made up there, and the direction here, we want it to be small. Smaller is better for this. It's not like accuracy where bigger is better. It is a metric where smaller is better. And then we just need to make one more thing, and it's going to look very similar to RMSE.DataFrame. Whoops, did I do that wrong? RMSE. Well, I can just write it. So what I'm going to do is I'm going to make one more function where I make the method. So RMSLE.data.frame. And so it has all this same stuff. So I'm making a method now for a data frame. And it's just metric summarizer. Metric summarizer, like this. Well, I don't need to know what's in it. I just need to know what we call here. So this is the stuff that I need. I need this stuff. I don't need the options because this is just normal. Like so. And so my metric name is RMSLE. The metric function is RMSLE_vec. I just made it. Data, truth. So here, I think does it have, no, we can just look at the article to see how we need to use rlang here so that we can pass these as names. So you do bang bang and quo truth, bang bang and quo estimate. And we see some of this doesn't apply because it's not a class metric. This one, we're not applying this to, this doesn't apply either. And we want to pass however people pass this in here, we'll pass this as well. Okay, so I think this is it. Let's see if I did it right. Okay, so I made a new metric. So if I wanted, I could make a metric set with RMSLE, as well as like a mean average percentage error. And so like I can now put this in a metric set if I want. However, this is a metric that should not be applied to something that's already on a log scale. Like that doesn't make a ton of sense. So what we want to do is we want to take this test data that I made, and I am going to, remember, it has test. If I look at price and the predicted price, these are on the log scale right here. So what I want to do is I want to change them. So if I say across C here, and I want to change them so they're now on the back on the real price scale, like this. So now I'm back on the real price scale. So this one I bet is a single room, you know, this one's a whole house maybe, et cetera, et cetera. So they're back on a price scale. And now I could do something like mean average percent error price prid. So this is telling me, you know, this is a metric that is built into Yardstick. It's in relative units, so it's relative to the price. What's the absolute percent error, mean absolute percent error, how wrong I am. And now moment of truth, root mean squared log error. Let's see, moment of truth, did it work? No. All right, it's almost working. Let's see what I did wrong here. That's right. Okay, so let's space this out a little bit. Squirt, mean, log, mean, there. Okay, that looks right to me. Function truth, okay. That looks right. Let's look and see what else I may have missed. RMSLE data frame, truth, data. There we go. Okay, let's try this again. Okay, let's try one more time. Moment of truth this time. Okay, 0.431. And that's actually the actual metric that was being evaluated on Sliced. And this is, you know, these are very close together, and like how exactly, you know, close are they? We could say, we can actually do this and see like how close or different are they for this particular example. So we can say RMSE price pred. So this is before the transformation and after. And so we can see how it is different, right? Because the math it is very close, right? Because you're like pushing things before and after the on and off the log scale, but it depends on like how many really high price things you have, and how the distributions are to how close exactly they are. So if you look at Slice, this is actually pretty competitive with how things are going. And so as a reminder, I'm not using, you know, XGBoost. This is a very straightforward, simple model, you know, tree-based model that's just like bootstrap aggregated. Nothing super fancy is happening in feature engineering here. Probably the best thing that's happening is that I'm using some of the text information and demonstrating here how to combine rectangular information, numeric, categorical, together with unstructured text information using feature engineering.
All right, so I got the custom metric to work there. And so that was the metric that was being used to evaluate prices on the original scale, on the scale of dollars, on Sliced this week. And it's a great example of how you can, if you are in a situation where you have something custom or specific that you want to use to evaluate your own models, you can use. I do want to highlight that I transformed price to the log scale for my modeling, because in this case, with that kind of distribution, I in almost all situations I've ever been in, the model will perform better if it is trained with it on the log scale. So and then if you want to make the predictions, you go back to the original scale, and in this case it was being evaluated on that scale with a metric that involved a log, so kind of back and forth a lot there. This particular model was not what would be considered a super high performing model typically, but it actually did pretty good compared to what most people got during the competition. And I think that's because of the way that I was able to incorporate the text information. That's often a really powerful tool, and in tidymodels, the support that we have for that is quite good. So I hope that this was helpful, and I will see you next time.